Okay, logistic regression is yet another technique borrowed from machine learning from the field of statistics. It's a powerful statistical way of modeling a binomial outcome with one or more explanatory variables. It measures the relationship between the categorical dependent variable and one or more independent variables by estimating probabilities using a logistic function, which is the cumulative logistic distribution. You'll first explore the theory behind logistic regression. You'll learn more about the differences with linear regression and what the logistic regression model looks like. You'll also discover some other things, but first, let's tackle logistic regression in R. You'll not only explore a dataset, but you also fit the logistic regression models using the powerful GLM function in R. Evaluate the results and hopefully understand how logistic regression works. So as the name already indicates, logistic regression is a regression analysis technique. Regression analysis is a set of statistical processes that you can use to estimate the relationships between or among variables. More specifically, you use this set of techniques to model and analyze the relationship between a dependent variable and one or more independent variables. Regression analysis helps you to understand how the typical value of the dependent variable changes when one of the independent variables is adjusted and others are held fixed. As you already read, there are various regression techniques. You can distinguish them by looking at three aspects: the number of independent variables, the type of dependent variables, and the shape of the regression line. Linear regression is one of the most widely known modeling techniques. It allows you, in short, to use a linear relationship to predict the average numerical value of y for a given value of x with a straight line. This line is called the regression line. As a consequence, the linear regression model is y equals ax plus b. The model assumes that the response variable y is quantitative. However, in many situations, the response variable is qualitative, or, in other words, categorical. For example, gender is qualitative, taking on values male or female. Predicting a qualitative response for an observation can be referred to as classifying that observation, since it involves assigning the observation to a category or class. On the other hand, the methods that are often used for classification first predict the probability of each of the categories of a qualitative variable as the basis for making the classification. Linear regression is not capable of predicting probability. If you use linear regression to model a binary response variable, for example, the resulting model may not restrict the predicted y values within 0 and 1. Here's where the logistic regression comes into play, where you get a probability score that reflects the probability of the occurrence of that event. Logistic regression is an instance of classification technique that you can use to predict a qualitative response. More specifically, logistic regression models the probability that gender belongs to a particular category. That means that if you're trying to do gender classification where the response gender falls into one of two categories, male or female, you'll use logistic regression models to estimate the probability that gender belongs to a particular category. For example, let's say the probability of gender given long hair can be written as probability is gender equals female given long hair. The values of probability for gender equals female long hair, abbreviated as the probability of long hair, will range between 0 and 1. Then for any given value of long hair, a prediction can be made for gender, given x as the explanatory variable and y as the response variable. How should you then model the relationship between the probability that y equals 1 and x equals x? A linear regression model represents these probabilities as probability of x equals beta 0, which is the intercept, plus beta 1, the slope, x. The problem with that approach is anytime a straight line is fit to a binary response that is coded as 0, 1, it will exceed, you have the possibility of exceeding 0 and 1. So to avoid this problem, you can use the logistic function to model the probability of x. That will give an output between 0 and 1. The logistic function will always produce an S-shaped curve, so regardless of the value of x, we will obtain a sensible prediction. So on the left we have our linear model, and we see what happens when we try to apply it to a 0 and 1. As we approach 1 and we go past it for these x values, we will start getting values above 1. Similarly, on the bottom, if we get very small values of x, we can go below 0. We fix this by using the logistic regression curve. It is similar to the sigmoid curve in its shape. It's just shifted between 0 and 1, and it goes infinitely in both directions of x, getting ever closer to either 1 or 0. So in a our logistic regression model, the left-hand side of the equation is called the logit. Increasing x by 1 unit changes the logit by beta 0. The amount that the probability of x changes due to a 1 unit change in x will depend on the current value of x. But regardless of the value of x, if beta 1 is positive, then increasing x will be associated with increasing the probability of x. And if beta 1 is negative, then increasing x will be associated with decreasing the probability of x. The coefficients of beta 0 and beta 1 are unknown and must be estimated based on the available training data. For logistic regression, you can use maximum likelihood, which is a powerful statistical technique. Let's refer back to our gender classification example. You seek estimates for beta 0 and beta 1 such that plugging these estimates into the model for probability x will yield a number close to 1 for all individuals who are female and a number close to 0 for all individuals who are not. In this section, you'll study an example of a binary logistic regression, which you'll tackle with the ISLR package in R, which will provide you with a data set and the GLM function, which is generally used to fit generalized linear models. Will be used to fit the logistic regression model. First thing to do is to install and load the ISLR package, which has all the data sets you're going to use. For this tutorial, you're going to work with the S-Market dataset within RStudio. The dataset shows daily percentage returns, the S&P 500 stock index between 2001 and 2005. Now, if you go onto Blackboard, I have an R file already there for you. And when you click on it, it should open up in RStudio and look like this. First thing you'll want to do is install all the packages we're going to use. So if you highlight all the installed .packages lines and hit run, it will install all those packages. I already have those installed, so I'm not going to run that. The next thing we're going to do is open the library that our data set is in. Then, let's see. Let's run this next line, and we can take a look at what the data looks like. So if we do View S-Market, it'll open on another tab all of our data. Go back to this. Okay, so the S-Market is a data frame with 1,250 observations on the following 9 variables. First one gives us a year between 2001 and 2005. And we have 5 lag variables. And that is the percentage return for the previous day. And then we have for 2 days previous, then 3 days previous, 4 days previous, 5 days previous. Then we have our volume of shares traded, number of daily shares traded in billions. We have today's percent return for today, and our last one is direction, to factor which levels down and up, indicating whether the market had a positive or negative return on a given day. So let's explore the data a little bit more in R. You can use the names function, and this will give you the column names that are used. So that tells us all the variables that we have in our data set. If you want to look at the top values in our data set, head function will give you first 6 values, or the first 6 observations of the data set, and tail will give you the last 6 observations. So let's start with some exploratory data analysis. First we took a look at the data set, but we can run some descriptive statistics using the summary function. So if we run the summary function, we can get all of our variables to tell us the minimum year, maximum year, mean, etc. for here. So let's look at today. Looks like it could have gone up by down by 4.9% or up by 5.7%, depending on that particular day. Let's see. Come down. So box plot we can develop to look for outliers, and then we'll check for missing data. So the summary function gives you a simple summary of each of the variables on the S-market data frame. You can see there's a number of lags, volume, today's price, and direction. We will use direction as a response variable, as that shows whether the market went up or down since the previous day. Data visualization is perhaps the fastest and most useful way to summarize and learn more about your data. So we'll start with looking at a box plot. This line of code should go. There we go. Zoom. Okay, so take a look at the box plot. Box captures the middle 50% of the data. The line shows the median, and the whiskers of the plot show the reasonable extent of data. Any dots outside the whiskers are good candidates for outliers. You can see that the lags in today all has a similar range. Otherwise, there's no sign of any outliers. Let's see. The next function we will run is to check for missingness. So let's see. Missing data can have a big impact on modeling. Thus, you can use a missing plot to get a quick idea of the amount of missing data in the dataset. The x-axis shows attributes and the y-axis shows the instances. Horizontal lines indicate missing data for an instance. Vertical blocks represent missing data for an attribute. And luckily, we have no missing data in this dataset. Okay. Next thing we'll do is we'll look at the correlations. We want to check correlations to determine if there is any overlap in the predictive power of our variables. So let's start calculating the correlation between each pair of numeric variables. Their pairwise correlations can be plotted in a correlation matrix plot to give to give an idea of which variables change together. So we have another library called CorePlot that we can run our correlation table. Try and click on it. Clear that out. Let's run this again. There we go. So it's kind of hard to see the faint colors, but a dot representation was used where blue represents positive correlation and red is negative. The larger the dot, the larger the correlation. You can see the matrix is symmetrical and that the diagonal are perfectly positively correlated because it shows the correlation of each variable with itself. Unfortunately, none of the variables are correlated with one another. Let's make a plot of the data. There's a pairs function which plots the variables in S market into a scatter plot matrix. So that one. Clear that one out first. Okay, let's try the pairs plot. Right. Should have run. Well, can't get that line of code to work yet. Let's see. There it goes. Okay, I don't know what the delay was. Zoom into that one. Okay, well, try to zoom in as much as possible on the pairs plot. In this case, we can see that direction, your binary response, is the color indicator. It looks like there's not much correlation going on here. Class variable is derived from the variable today, so up and down seems to make a good division. Other than that, there's not much going on. But direction, you can see, gets separated into a binary variable pretty well. Okay. So the next thing we're going to do is build the model. We're going to use the GLM function. Now you can call the glm.fit function. First argument that you pass to this function is an R formula. In this case, the formula indicates that direction is the response, while lag and volume variables are the predictors. As you saw in the introduction, GLM is generally used to fit generalized linear models. However, in this case, you need to make it clear that you want to fit a logistic regression model. We resolve this by setting the family argument to binomial. So I'm going to run the GLM model here, but the family equals binomial tells R that we want to run a logistic regression. So we run it, and it will save it over here as glm.fit. The next thing we want to do is summarize our results. We can use the summary function of our model to check to see if the variables are significant. So this summarizes it. It gives our coefficients for each of our variables as well as the p-value. You'll notice that because it's logistic regression, we're not going to get the ANOVA results that we get with linear regression. We do get this AIC value that is a goodness of fit indicator. But the first thing we should notice is there is no significant p-values for any of our variables. So this isn't a particularly good model. Let's see. So the next thing we want to do is prediction. So we can see how not this is a particularly good model, but how well can it predict future values for the stock market. And we might want to check and adjust the threshold to get better predictive power. Up. So when we do prediction, we're going to use basically the output of that to set it up. Run this. Okay. So first set of code, we are looking at the first 5 probabilities, and they are very close to 50%. So now I'm going to make a prediction based on that 50%. So that's where we get this value from. Since each of these values was near 50%, we set 0.5 as our threshold for when we're predicting. Basically, it's kind of like in Excel where we have an if statement. If the probability is less than 0.5, it's going to be down, and if it's greater than 0.5, it's going to be up. So GLM pred will give us a little table here, and this is called a confusion matrix. The confusion matrix is going to tell us the true negatives and the true positives. Basically, the diagonals give us when our prediction was correct, and the other diagonal gives us our prediction when it was incorrect. So true negatives is equal to 145, false positives is equal to 141, false negatives is equal to 457, true positives is equal to 507. We can use those values to calculate all of our accuracy and predictive powers for our model. Accuracy is how often is the classifier correct. So you add the total positives plus the true positives plus the true negatives and divide by the total. Also calculate out our misclassification rate, which is overall how often is it wrong. So that's our false positives plus our false negatives divided by total. We can also take our accuracy and subtract it from 1. This is also known as the error rate. We can get our true positive rate when it's actually true. How often does it predict yes? False positive rate when it's actually not true. How often does it predict yes? Specificity when it's actually no. How often does it predict no? Finally, precision when it predicts yes. How often is it correct? So this is our coefficients from it, but we already talked about them. None of the coefficients are useful right now because none of the p-values are significant. But as another little trick, I will show you. Run this. This last little bit of code takes a little bit of time, but the cool thing is it will create your confusion matrix and then calculate all those values for you. We can see that our model has about 52% accuracy. It also gives us our sensitivity and specificity, our positive, false positive, and negative. So It's nice because otherwise you have to manually calculate all those off of the confusion matrix, and this will give you a easier way to do that. So the last thing I want to talk about is your assignment. So your assignment for this week, you have started as an analyst at a university. The dean has asked you to analyze students that have been accepted or declined for the graduate program. Basically, you're going to do everything we just did in this tutorial on a new set of data. It's a pretty easy data set. The admit will be your response variable, and then you have 3 explanatory variables: their GRE score, their GPA, and their rank. So what you'll need to do is modify the script here to fit the new data set, and then create all of the required things for the assignment. So you'll explore your data, you'll create a predictive model, you'll develop a confusion matrix, and then you'll interpret your analysis. So for all the charts that you've created, explain what they mean, summary statistics, explain, interpret your regression output, whether the p-values are statistically significant, and if they are, what do the coefficients mean, and then also your confusion matrix, explain them in your report. So how accurate is your model, and how the sensitivity, explain the sensitivity and specificity of your model. And that should be everything you need for this week.